Hi everyone, my name is Ming Zhou and I'm with MBA Scientific Consultants. We are a full-service analytical microscopy lab located in Atlanta, Georgia. We work with stack testing groups and laboratories to provide electron microscopy, particle sizing, and material characterization services. We have been in business for 26 years. Beginning today, we will be offering a series of webinars that focuses on microscopy particle sizing and particle identification to illustrate how these applications benefit the stack testing industry. For this webinar, we will focus on SEM analysis of method 201A filters. I want to introduce our speaker for today, Tim Vanderwood. Tim is one of our executive directors at MBA Scientific Consultants. Tim is also one of the pioneers in introducing electron microscopy particle sizing to the stack testing industry, and he's very active in stack testing professional organizations such as SES and CAPCA. He has been helping stack testing clients solve particle sizing and contamination issues for the past 20 years. And now I'm going to hand it over to Tim.
Thank you, Ming. Recently as last week, in fact, I gave this talk to the SES meeting in Alabama, and we talked about what we found on method 201A catches. It turned out to be of great interest to the community, and I thought we would repeat it here. I began my talk last week by admitting my prejudices. I have, for something like 40 years now, been characterizing particulate samples and individual particles using microscopy and many other techniques. And when I came to the stack testing industry, I was amazed that someone would characterize a particulate sample by weighing it. There is so much more information to be learned that I thought we would talk something about what we can learn about particulate samples, and we would use as an example method 201A catches, both the PM 2.5 and the PM 10 fractions. I'll begin by introducing you to the microscope that we use to do this kind of work. We use a scanning electron microscope, and here's a picture of one with the operator. It's a relatively large piece of equipment, although smaller types do occur now. You must be careful a little bit in the type of instrument that you bring to this analysis, because it has to have a significant resolving power, certainly enough to see down to about 0.1 micron particles and individually resolve them. There's a sense in which the SEM is just a big camera. So one of the things you do with it is take pictures. These are pictures of particles. There are two imaging modes that are commonly used, and you see them both here. On the left is what's called a secondary electron image, and on the right, a backscattered electron image. These are the same fields of view. The secondary electron image is formed from electrons that are given off by the sample under electron bombardment. The backscattered electron image is formed, as you might infer, from electrons that bounce off the sample. So the two different imaging modes highlight two different things. The advantage of the backscatter electron mode is that it highlights the Z contrast, or the atomic number of the particulate, so that you can see that this particulate, which is principally aluminosilicates, shows up bright against the background of a polycarbonate filter, which is principally carbon and oxygen. I've shown a polycarbonate filter here because that's the filter that is most useful for stack testing applications in method 5, but it's also possible to take images of particles on a glass fiber filter, and that's what's shown here. This is a coal-fired power plant, and you can see the spherical aluminosilicate fly ash easily against the fibers of the filter. Not only can the instrument take pictures, but it can provide analysis. It can tell you what the particles that you're looking at are. Here we see an example. This is a somewhat fuzzy field of view image of particulate from a different coal-fired power plant, and there's three different kinds of material present and identified here. You can see the top EDS spectrum off to the right shows an aluminosilicate. Those are the spherical particles that you see in this field of view. They are aluminosilicate fly ash. The nice long crystals that you see are calcium sulfate, gypsum, and you can see that's the middle spectrum on the right. And then finally, the irregular somewhat dark particles in the bottom part of the image are either carbon ash, or perhaps activated carbon added to the system as a sorbent. You see they are composed of oxygen. So the SEM can provide not only images of the sample you're looking at, it can also provide an analysis and tell you what those particles are. You can use software to extract the particles from the image, and this is an example of that. You see on the left the two images we showed before, and you see on the right what the computer software now has identified as particles on this sample. They are given different colors. From this information, from these particles, the computer can extract all the two-dimensional morphological information you might want. The simplest is the area of the particles, but also maximum and minimum diameters, aspect ratios, roughness, typical parameters like that. Unfortunately, for the particles on a glass fiber filter, a quartz fiber filter, we do not have it as yet software that can recognize particles against the background of the filter. However, people are excellent image processors, so someone can sit with that image and outline the particles in the image and record that to software, which can then perform the same sorts of calculations of two-dimensional morphological parameters. Again, most importantly, size and average diameter. And that's what you see on the right, the result of someone manually defining and outlining the particles on this filter. So if we turn this tool to looking at method 201A catches, what do we find? This slide shows the results of the analysis of 3 different fractions of method 201A catches from 5 different sources. The method 201A uses cyclones to separate out particles nominally larger than 10 microns, and then a second cyclone to pass particles nominally smaller than 2.5, and particles between 2.5 and 10 microns are caught between them. PM10 in this setup is everything that is not rejected by the 10 micron cyclone, and PM 2.5 is everything not rejected by the 2.5 micron cyclone. In this case, we're looking at the rinse only. Method 201A has a filter after the final cyclone, but we're looking at just the rinse at this point. So some things begin to jump out at you. First is that the greater than 10 fraction is probably pretty close to right. There are somewhere between 75 and 100% of the particles are particle mass, which is what's shown here, are greater than 10 microns. So that's fairly accurate. Things get a little more interesting in the intermediate fraction. Now some 15% of the material to 98% of the material is still greater than PM10, so that this fraction, which now is included in the PM10 fraction, does include contribution from particles larger than 10. The most interesting part of this is what's going on in the PM 2.5 fraction, the less than 2.5 micron fraction. From these 5 sources, somewhere between 1 and 15% of the material is actually PM 2.5, that is, has a diameter less than 2.5 microns. Most of the material is greater than 2.5. 85 to 99% of the material mass is actually larger than 2.5 microns in physical diameter, which is what's measured here. So to summarize that, again, the greater than 10 micron fraction, 50 to 100% is actually greater than 10. For the 2.5 micron fraction, the PM 2.5, 85 to 100% of the material mass has diameters greater than 2.5 microns. The question is, what's going on? The normal understanding of 2.5 microns is that particles should be smaller than that, and yet we find the vast majority of the material in this fraction has sizes greater than 2.5 microns. 3 possibilities to explain this phenomenon suggest themselves. One is contamination, and that the samples have been contaminated. and material from outside the stack being tested is made it into the sample either during sampling, sample preparation, or sample weighing. It has been a criticism of the SEM method is that it actually measures the physical diameter of the particles, and PM 2.5 is defined as aerodynamic diameter. So perhaps what we're seeing here is the difference between physical and aerodynamic diameter. And if it's possible, we can check to see if the physical diameter and the aerodynamic diameter differences explain what we're seeing in the 2.5 micron fraction. The third possibility is that what we're seeing, this large contribution from particles larger than 2.5 microns, is inherent in method 201A. So let's look at these in turn. Contamination. It can be a problem with low catch weight samples, and this is turning up in other areas of particulate measurement in stacks, particularly in method 202, where the condensable fraction is counted as part of PM 2.5, and sources are now so clean that this condensable fraction is very small. And it's turning out to be nearly impossible to measure against background contamination and biases in the method. EPA has recently put out a best practices document to help people get around this problem in method 202 samples, but we can see that it's going to be a problem in method 201A samples, particularly with very light catches. In this particular example, sources 3, 4, and 5, those which had the lowest fraction of material that measured less than 2.5 microns in diameter, these had a total catch weight of less than or equal to 1 milligram. The acetone blanks, that is the reagent blank used to rinse this material out and catch it to weigh it, was on the order of 0.5 milligram. So there's a significant chance for contamination in these very, very lightweight samples. So perhaps the majority of the large particles in the 2.5 micron fraction are contamination, particularly in samples 3, 4, and 5, which had the very low catch weights. Certainly there are contaminant particles present. This is a trichome in a low catch weight PM 2.5 sample. This is from source 3. A trichome is a leaf hair. This material, which is very large, it's over 50 microns in longest dimension, is certainly not originating in the stack. This is a contaminant from the environment. But you can't explain all of the greater than 2.5 mass in this ostensibly less than 2.5 micron catch by contamination. These are also particles from low catch weight PM 2.5 fractions. On the left is a silicate fly ash particle. You can see that that particle is almost 40 microns in diameter. In the middle is a carbon ash particle, a graphite particle. You can see that this particle is 50 microns or so in longest diameter. And on the right, this is actually on the PM 2.5 filter rather than in the rinse catch. This is a combination carbon and sulfate particle that's associated with the stack. So these three particles are way bigger than 2.5 microns diameter, and they are certainly associated with the stack. So it can't all be contamination. The second possibility was that there are differences between the physical and aerodynamic diameter, and those may account for the finding of all of these big particles in the less than 2.5 micron fraction. That is, their aerodynamic diameter may actually be less than 2.5, even though their physical diameter is much larger. It is possible to relate the geometric diameter or the physical diameter to the aerodynamic diameter, and this is the equation through which you do that. You need to know the geometric diameter, the particle density, the standard density, which goes into aerodynamic equation. The standard particle is 1. So the standard density is 1 gram per cubic centimeter. You need to know the two-dimensional particle perimeter and the particle cross-sectional area. These equations come from aerodynamics. If you need to know the aerodynamic diameter of the cross-section of a wing, for instance, you would apply this equation. So the things you need to know are the particle density and some two-dimensional particle parameters, the perimeter and the cross-sectional area. here are the densities of some common stack particles. This is carbon ash, graphite, silicate fly ash, which we don't have a standard density for, but silicate minerals, which are of the same composition, are about 2.5 to 2.8. Silicate glass, which has the same composition and is close in physical structure to silicate fly ash, has a density of about 2.5, and gypsum has a density of 2.3. So these three most common components, at least of coal-fired power plants and of the samples that we examined here, all have densities between 2.3 and 2.8. And we're just going to take a density of 2.6 to put in that equation. If you recall from the equation, let me go back up to it, you're actually looking at the square root of the density. So the density doesn't have a huge effect. So here are the densities. So we have a way of getting at the densities that we need for that equation. We also needed the perimeter of the particles and their projected area. Those two parameters are recorded during the particle analysis by the software or by the human if a human is doing it. So you can measure the perimeter and you can measure the area. So we have everything that we need to go into that equation to convert geometric diameter to aerodynamic diameter. These are the results. The top table is what we've seen before, the geometric diameter measured by the microscope in the less than 2.5 micron fraction. And the bottom table is the same particle data set converted to aerodynamic diameter particle by particle. So we can see that it doesn't actually make things better. In some cases, it makes things worse because the higher density tends to make particles have a slightly larger aerodynamic diameter than they do geometric diameter. So we can see that now for the PM 2.5 fraction, the mass of the material on this catch, which is ostensibly less than 2.5 microns in diameter, ranges now from about 1% up to about 9%. So at least for these samples, the difference between aerodynamic and geometric diameter is not significant, and it cannot explain the large amount of mass that is in particles with diameters greater than 2.5 microns. So the final possibility is what we're finding on these filters, something that is inherent in the method. That is it something that is actually part of the definition, it's part of what's going to appear in all samples. This plot here shows an acceptable window for a PM10 cyclone. That is the percent efficiency of collecting a particle has to fall in the gap that you see between the lower diameter and the upper diameter. So it's centered around 10, but it goes up pretty high. It drops down a little bit, and you can have a aerodynamic efficiency of only 90% for particles that are almost 50 microns. So that there is some possibility in the cyclones, which have very wide cuts, of passing particles larger than you intended, or you would at least expect, into the smaller fraction. Moving along to some real fractions. This is the collection efficiency of actual PM 2.5 and PM 10 cyclones used in method 201A. The efficiency curves look fairly benign. That is, they are symmetrical about the cut point. So you can see that for PM 10, the collection efficiency is symmetrical around 10, and for PM 2.5, the collection efficiency is symmetrical around 2.5. Let's talk about these curves a little bit. This is the probability of capturing a particle of a given diameter in each one of these cyclones. So you can see that the collection efficiency is not a step function. That is, that the collection efficiency of a PM10 cyclone, it doesn't mean that you have a 100% chance of collecting all the 10 micron particles and above, and a 0% chance of collecting all of the particles smaller than 10 microns. In this cyclone, you have a 90% chance of collecting a particle here, say 50 microns, and a 5 or 10% chance of collecting a particle as small as 7 or 8 microns. But it does look fairly symmetrical. It looks fairly benign. There is an effect that the larger particles that you collect have a higher effect on the mass than the smaller particles that you don't collect. But all in all, it looks relatively benign. It looks much less benign if you change the scale. If you notice in the previous slide, the horizontal scale is on a log scale. If we change that to a linear scale, it looks a little less benign, and you can see that the collection efficiency of collecting pretty large particles is significant. And for PM10, the possibility of passing pretty large particles is pretty large. If you combine these two cyclone efficiencies, these cyclones are stacked in method 201A, so that the material, the particles that make it into the collection of PM10, that is less than 2.5 microns, have to pass both of these cyclones. So if you calculate the probability of each particle size passing these cyclones to get the probability of ending up in the PM 2.5 fraction, you get a curve something like this. So that a particle of 5 microns has about a 10% chance of getting into the PM 2.5 fraction. A particle of 10 microns has about a 1% chance of getting into the 2.5 micron sample. And even larger particles have a non-zero probability of ending up in PM 2.5. So what does that mean if we have an actual sample? Here's a model sample particle size distribution. It's based on the coal-fired power plant sample that we've actually analyzed. Particle size distributions are typically log normal. This is a log normal fit to actual data extended out to 25 microns and dropping down to 0.1 microns, which is the lower limit of the size that we usually measure. So that there are a lot of particles that are greater than 2.5 microns, but their probability is pretty small. You have 1 in 10,000. 1 in 10,000 particles is 10 microns, and it gets even smaller as you get bigger. This is the number distribution. Another way of looking at it, which is a little more illuminating, is to look at the mass distribution. These particles have been modeled as spheres so that the mass is proportional to volume, which is a cubic function of diameter, so that the mass distribution doesn't look quite the same. This is now very little of the mass is less than 2.5. A very small fraction of the mass is less than 2.5. And the significant fraction of the mass is in particles that are larger than 2.5. So if we challenge a model PM10 cyclone stack with a particle size distribution that looks like this, that is, we put that particle size distribution through the cyclone, what do we end up getting at the other end? This shows the cumulative mass distribution in the PM 2.5 for this model situation between 0.1 and 25 microns. You can see here that at 2.5 microns, about 30%, 40% of the mass fraction is less than 2.5. We're now looking at the cumulative mass distribution, so this would be 100%. But that means that something like 50 to 60 to 70 to 80% of the mass collected in the PM 2.5 fraction is actually from particles greater than 2.5 microns. So that at least a good deal of what we're seeing in these actual PM 2.5 catches is from particles that are greater than 2.5 microns, typically more than half. So back to the question of what's going on. The first question we asked was, could it be contamination? And for very light catches, this can be an issue. And it's showing up more and more in the attempts to define particulate populations by weighing them. It's seen here in method 201A in very light catches. It's seen in method 202 in light catches. Just the ability to be clean enough to have a clean sample to weigh in the face of environmental background. When you're talking about weighing samples that are a milligram or less is a significant challenge to the analyst. Could it be the differences between physical and aerodynamic diameter? For normal stack materials, as we showed here, it's not a significant difference. The change from physical to aerodynamic diameter does not have a big effect on PM 2.5. And in some cases, there when you calculate the aerodynamic diameter, you end up with a lower mass in PM 2.5 than you did when you just used the physical or geometric diameter. Finally, we asked the question, could this be due to the method itself? And the answer to that question is yes. Model calculations indicate that for a stack sample, you may have greater than half of the material that's ending up in as PM 2.5 is from particles greater than 2.5 microns in diameter. That goes to the question of whether method 201A is suitable for its use. The reason for doing these sorts of analyses in stack samples is to protect human health and welfare. In this case, human health from fine particles are known to cause lung disease and perhaps some other things. And that welfare is fine particles are known to act as condensation nuclei in the atmosphere and to cause haze and smog. The fitness of the method is to try to measure PM 2.5 so that you can regulate both to improve human health and improve human welfare. Well, we see some limitations in the method in that it doesn't actually measure PM 2.5 very well. It grossly overestimates it. The other question comes around suitability for use for protecting human health and welfare. Consider a PM 2.5 sample that is composed all of 2 micron particles and a sample of the same weight composed all of 0.2 micron particles. These would be given the same weight in importance in defending human health and welfare, even though they are very different particle populations. For human health, the insult to the lung is actually not the mass of particulate, it is the surface area of the particulate. And the surface area of a particulate sample that is composed of 0.2 micron particles is 10 times the surface area of the same weight of particulate composed of 2 micron particles. So this is a factor of 10 difference in impact on human health that is not addressed by the method. For human welfare, the haze formation, the difference is even starker. Consider those 2 same particle populations, one of all 0.2 micron particles and the same mass of 2 micron particles. Again, all of them, both samples defined as PM 2.5 and found equal. Well, the haze formation is dependent on condensation nuclei, and condensation nuclei depends on the number of particles, not the mass. The number of 0.2 micron particles in this sample will be 1,000 times the number of 2 micron particles in the sample. So the effect on haze formation of the 0.2 micron particles is 1,000 times the effect of the 2 micron particles. So the impact on human welfare is different by a factor of 1,000. So in conclusion, background and contamination is an issue for low catch weight PM 2.5 fractions, just as it is for method 202 catches. For historical reasons, PM 2.5 is defined using aerodynamic diameter. And that means by the method that usually the majority of the particulate caught, or possibly the majority of the particulate caught in a PM 2.5 fraction is going to be for particulate that is larger than 2.5 microns. Even the aerodynamic diameter is larger than 2.5 microns. We just discussed if these historical reasons for defining PM 2.5 using aerodynamic diameter and cyclones still apply. And I think that's questionable because it disguises what could be huge differences in human health and human welfare impact of the PM 2.5 fraction when all you've done is weigh it. I did note that during the meeting that I attended last week, there was discussion of doing away with the PM10 cyclone in method 201A, since PM 2.5 is what we're really after and nobody cares much about PM10 anymore. I would point out that removing the 10 micron cyclone from in front of the PM 2.5 cyclone will only make matters worse, and emitters are going to be faced, if this happens, with a sudden increase in PM 2.5 that has nothing to do with the way they operate their facilities, but has only to do with the fact that we've now removed a cyclone from in front of the PM 2.5 cyclone, and that cyclone removed the majority of the particles larger than than 10 microns. And those particles will now be presented to the 2.5 micron cyclone, and some of them are going to make their way into the PM10 fraction. So thank you very much for your attention.
Hi, Tim. Thank you for the great presentation. I hope you folks enjoyed it. And if you have any question, please feel free to contact us at 770-662-8509. And also feel free to give us an email as well. Here's our contact information on our web. I'll show you real quick. So this concludes our webinar for today, and we will be doing more of this sorts of webinar in the coming months. Please stay tuned. Thank you. Bye-bye.
Thank you, Bing. Bye-bye.
Bye-bye.